So vapor power cycles, 10.73. Coal-fired steam turbine power plants operate on an ideal Rankine cycle, producing 175 megawatts of electric power. Steam enters a turbine at 7 megapascals and 550 Celsius. The condenser operates at a pressure of 15 kilopascals. The coal has a heating value of 29,000 kilojoules per kilogram, and assuming 85% of this energy is transformed to steam in the boiler, the electric generator has efficiency of 96%. We need to determine the overall plant efficiency and the required rate of coal to be supplied to the system. All right, it's a long question, and I would like you guys to pay extra attention and stop me when you have any questions. All right, week 9, problem 10.23, and we're dealing with Rankine cycle. Rankine cycle, 2 isentropics, 2 isobarics. Okay, so it's the same thing as the Brayton, but this time dealing with water, not with air. Okay, I'm gonna get a drawing that I did before the other class that was actually quite useful for us. Just want to repeat the. Okay, so let's look at this system. What do we have? We have a compressor, which in some cases we're also going to see as a pump, right? They are not quite the same thing, but for the purpose of our course, you can think of them as the same thing. So we're going to have liquid water on our first state, and we're going to put that liquid water through a compressor or a pump, okay? And then we're going to have compressed water over here in our second state. Now, this is already very different from before. Why? Because before we had air. And if you compress air, we're going to be changing not only the pressure, but also the volume, right? In the case of water, it's an incompressible fluid. So the change in volume when we compress it is going to be minimal, right? It's going to be almost nothing, barely noticeable. So what does change from here to here is pretty much the pressure. The volume stays the same. And we're going to use that to our advantage when we're solving these. Okay, then our heat addition process happens in a boiler. Why boiler? Because literally we're boiling water. We want water to go from liquid phase into the vapor phase so that we can have water with a high quality of energy. So when it leaves the boiler, we're in stage 3. This guy can be superheated, it can be saturated vapor, it can be mixture. It depends. On an ideal case, it's always going to be superheated, but we can't be sure. We need to always check. Okay, and then we're going to go through our turbine. Which is going to use this energy to give us an output, right? Energy output, just like before. It's going to leave the turbine at a certain state here. In the case of this problem specifically, this energy goes into a generator. And this generator then outputs electricity, right? So we're giving energy in the form of coal here on the boiler, and then we're getting energy in the form of electricity by the end of it. The trick is that when it leaves the turbine, right, we don't have 100% liquid. We can have still superheated state, we can have a saturated vapor, we can have a mixture. But if it's not 100% liquid, we can't just put it back into the compressor and the pump, right? That's going to bring us some problems. One of them is that we're going to have a variable chamber in there to account for the difference in volume. So what we do is we have our heat rejection. Not to say this doesn't have a lot of useful energy. So we're going to have a condenser here. And the condenser is literally doing what you would expect. It's condensing the vapor back into water. So the job of the condenser is to get all the water that's not in the vapor, that's in the vapor form, and make sure that when it reaches state 1 again to go back into the compressor, it's all liquid form again. All right, so mind you guys that just like before, we have to input some work or some energy, give some energy to our compressor for it to be able to compress our liquid. Just like before, we need to give heat. So we give energy in the form of heat here on the boiler. Just like before, we have an output of energy in the form of work through the turbine. And just like before, we have the output of heat through the condenser. Okay, so in that case, it didn't change much. Now let's have a look at the TS diagram, see how this guy's going to behave. Just open up the chat to make sure. Yeah, just open the chat. Yeah. All right, awesome. So how does this going to look on our temperature over entropy diagram? Remember this, your old friend, dome? Here it is again. Okay, we're going to start here. Okay, why there? Because I know that that's 100% liquid. It could be compressed, that's fine. If you guys recall, whenever we had something that was compressed, what we did is we approximated it to the saturated liquid form. Because the enthalpy doesn't change much, is precisely because the volume doesn't change and so forth and so forth. Okay, so our first state, we can always assume it to be saturated liquid. And then we're going to compress it, so it's going to be an isentropic compression. It's the first isentropic compression. It's going to go upwards, like so. Okay, so that's our second state right there. Okay, now we have an isobaric heat addition. And if you guys recall, our saturation line, it goes something like this. Then once it reaches the dome, it goes straight. And once it reaches the dome, it goes like that again. That's our saturation line there. So if we want an isobaric heat addition, it means we have to follow that guy all the way to the end, right? So I'm going to follow this guy as I'm adding heat. Then I reach the line, and that means that now I'm evaporating water. Now have less liquid, and I have no liquid whatsoever. I have all vapor. And then I can stop here, or I can keep going. And I'm not sure in our case what's happening. I have to check to be able to be sure of what's happening. I'm going to end up somewhere here, okay? Whether it's superheated, saturated, mixture, I'm not sure. I'm going to have to see. And then we're going to have our, so that's our isobaric process. Now we have another isentropic. So we have the isentropic going down, so no change in S. And we're going to go straight down to our state 4. And I've stopped there because I know it's going to be another isobaric change from 4 to 1, so it has to be on the same line because of the saturation line once again. And the saturation line will go like this, down like this. Yeah, so that's our cycle right there. Okay, now a couple of things to keep in mind. Whether 3 is here or here or here, I don't know yet. Whether 4 is here, here, or here, I don't know yet. We need to find that out as we're doing the problem with the properties that we're given. What I can tell you guys before we even get started is we can have a look at what are the energy states around this process. Right? Let's just do the energy states like I like to do with you guys. All right, this is just qualitative energy states, not worry about numbers. My state 1 is the lowest state in energy I'm going to have. It's just liquid water, saturated water. I'm going to compress that water, and I'm going to put some work into it to compress it. But little changes, right? Since the compressor has to put little work to this work here is little because there's no change in volume. Then I'm going to have my boiler, and then I'm going to all the liquid water that's in here I'm going to transform into vapor. So this is a big jump in energy right here. And then I'm going to have my turbine working, getting out that energy, and I'm going to stop on 4. But note that 4 is still a vapor. So to be able to go all the way back to 1, there's a big leap that I have to, big energy leap I have to undertake, right? To go all the way down, all the way up there. So 4 is definitely above 2 because this is vapor and this is liquid. This is compressed, this is not compressed, but this is vapor, and vapor we know. Just look at our tables, we can know this is way higher energy state than this guy is. So we have to go way down to be able to go all the way back to state 1. You guys as engineers, you're probably thinking already, well, can we just take some of that energy and put it back into our system? Definitely can, we definitely will soon enough. Just hold tight. Okay, so now let's look at the information that was given. We had the following. Steam enters the turbine at 7 megapascals and 550 Celsius. So where is it entering the turbine? It's right here. That's where it enters the turbine. So that means that T3 is 550. And my P3 is 7 megapascals. But if it's an isobaric process from 2 to 3, that means that my P2 is also 7 megapascals. What else? The condenser operates at a pressure of 15 kilopascals. So this guy here, it's operating at 15 kilopascals, right? Since this guy is operating in this, it's an isobaric process, that means that both P1 and P4 are the same. P4 equals P1, and they are both 15 kilopascals. Okay, that's what we know. Let's see if there's anything else, any other information. We have the 85% of the steam. So when we're putting energy from the coal into our boiler, we have an efficiency of 85% over here. And one generator has an efficiency of 96%. Okay, so what we being asked is, what's the overall efficiency of this whole thing here? It's the overall efficiency. The overall efficiency is always a combination of the individual efficiencies, right? So in this case, we have the efficiency of coal giving energy to the water, which is 85%. So that's going to be, let's just put efficiency of coal. Yeah, just do coal. Be the boiler too. We have the generator, which is taking this work and transforming it into electric energy, and that's operating at 96%. And we have the actual plant, right? The one that's getting the water, compressing, boiling it up, using turbine, condensing, doing that. So that's the thermal efficiency of our cycle. We have this 85%, we have this 96%. What we don't have is this guy. But we know how to find it, right? We can do Q in minus Q out, or we can do work of the turbine minus work of the compressor, right? Either way. So what we need to do is solve this cycle to be able to find the efficiency, to be able to go back, plug this in, and find the overall efficiency of the whole thing. Now, on these, just like before, I'm going to give you a tip. Try to solve everything, all the states, 1, 2, 3, 4, and then afterwards grab what you're looking for. It's going to be way easier for you guys. Okay, so if you want to take a screenshot, go for it. I'm going to get a new page and I'm going to start solving the states. I want to find the enthalpy for state 1, state 2, 3, and 4. With the enthalpy, I can find the work of the compressor, or I can find my Q in here, or I can find my work of the turbine, or I can find my Q rejection here. Right, so if I have enthalpy, I can do enthalpy of this minus this to find this, enthalpy of this minus this to find this, or enthalpy of this to find this, and so forth. Okay, screenshot time. Let's move on to the next page. Okay, I have 4 states I want to define. This is still 10.23, and we're still recording. Okay, so let's do state 1. State number 1. What do we know about state number 1? Well, just looking from the graph we looked before, we know that our state number 1 is at 15. State number 1 is at 15 kilopascals. And I also know it's a saturated liquid. Pablo, what if it's compressed? Well, we talked about that, right? If it's compressed, we can approximate it to the saturated liquid because the properties don't change that much for a incompressible fluid. So I can go straight to my table A5, the one you guys have been missing for so long. I can look at 15 kilopascals and I can grab H1, which is going to be H sat for liquid. And this guy is, what do I have here? 225.94. Okay, and as a matter of fact, what you can grab is everything. Right? You can grab entropy, temperature, specific volumes in the lot. Okay, when I was solving this, I actually grabbed way more things than I needed, just because it's easier to do it once you're there than actually have to go back afterwards. The other thing I'm going to grab is 1014. That's the specific volume for state 1. Okay, so state 1 is 100% defined, all good. Let's move on to state 2. Now, state 2 is going to be different. Okay, it's simple, but it's different. So make sure you pay attention. Ask me if you're not sure. But state 2, from now on, the way we're going to do is, since it's incompressible, remember I told you we can use that to our advantage. What I'm going to do is I'm going to calculate the work of the compressor. Okay, because the work of the compressor is 2 ways I can define it. It's going to be the difference from state 2 to state 1. That's the work of the compressor. But the work of the compressor is also, if you guys recall, work is going to be PdV from 1 to 2. Now this dV is very, very small, right? Because this dV is the one that I told you because it's incompressible. But my pressure is changing as you go from 1 to 2. So because it's incompressible, let's actually do because compressible. This guy is approximately delta P V1, right? Because whatever V2 is, V1 minus V2 is not going to be much different than V1 because my change is very little. So what I can do is work on my compressor will be, what's the difference in pressure? Well, I'm going from 15 kilopascals all the way to 7 megapascals. So 7 times 10 to the third kilopascals minus 15 kilopascals times 0.001014. And that is kilopascals times meters cubed over kilograms. You guys will recall that Pascal times meters cubed, that's newtons over meters squared. That's just newtons times meters. That's a joule. So that's kilojoules over kilograms. And this is precisely 7.08 kilojoules per kilograms. Why am I doing this? Because now I can actually use this information to my advantage, because I can go and use this information in here and calculate what is my H2, my enthalpy 2, which is what I'm looking for, right? So note that the only thing that I knew about state 2 before I did this was the pressure, which was 7 megapascals. Now I'm going to know the pressure and the enthalpy. And once I know that, I have the whole thing defined, right? So my enthalpy 2 equals my enthalpy 1 plus the work on the compressor, which equals 225 plus the 7, it's 233.03 kilojoules per kilograms. Okay, so we're all good on second state. We have the enthalpy that we're looking for. We're happy. All right, now this is different because we never did this before, but from now on, this is what we're going to do to be able to go from one state to the other, from state 1 to 2, because of this property of water, this little change in volume. Okay, so now that we have state 1 and state 2 defined, we can go ahead and move into state 3.
Sorry, Pablo, quick question.
Yep.
Can't you use the fact that it's isentropic? Oh, it's not, yeah.
No, it is isentropic. It is isentropic. You can use the fact that it's isentropic. Yes, you can do that, and it's going to render you a similar result to the point of like the 1% error or even less. This is just quicker, but you could do that as well. You see that we're going to do that on the next stage, and you'll see why I find this one to be easier. Right? You'll see in just a second. But yes, you could have. State 3. What do we know about state 3? We know the temperature, 550. Yeah, 550 Celsius. We know the pressure, 7 megapascals. And we have this guy completely defined. We have 2 things for it already. Now, if you guys recall, I don't think we need to do this. We did this a lot of times already. We can go to table A7. I'll do it just for the sake of it. I'll do it. Let's go to the table, property table. And we're going to look at 7 megapascals. So that's going to be 7,000 kilopascals. 7,000 kilopascals. The T set saturated temperature at 7 megapascals, it's 285. Our temperature is 550. So our temperature is above saturated temperature, which means that our state is a superheated state, right? So because my T3 is above my T set, superheated. And because this is superheated, I can go, instead of looking at table A5, I'm going to look at table A6. And on table A6, I can grab my enthalpy. And just, was it James that was speaking before? Just like James said, I think it was James. I can grab my entropy, because that's what I'm going to use to define my fourth state. Again, when I did this, I grabbed a specific volume, I grabbed all the lots. But since we're limited on the space here, there's no point in putting information that we're not going to use. 6 kilojoules per kilograms. And my entropy is 6.9. Okay, now this is a thing, right? When we were looking at it before, put up this graph here. When we were looking at it before, this guy is also isentropic, okay? This guy's gonna be a compressed fluid. So it's a different beast from the one that we're used to calculating. So we can do that trick with the compressor work that we just did. But from this guy to this guy, this is now a vapor, right? So the volume here is gonna be, it's gonna change substantially, right? It's gonna be a significant volume reduction from here to here. So in this case, we can't use the same trick because it's not going to be incompressible. What we can do is, just like was proposed, is use the fact that it's an isentropic transformation. From 3 to 4, we're not changing entropy. So therefore, state 4 has two things that we know already. Has the pressure, 15 kilopascals, and also has the entropy, which is the same as, which is 6.9. Yep. So that's exactly what we're about to do. And you'll see why you can do this, but you might want to avoid it when you can. All right, so state 4, what do we know about state 4? We know two things about state 4. You know, pressure is 15 kilopascals, same one as P1. And we know the entropy of state 4 is the same as entropy in state 3. So that's 6.9. Later on, this is going to vary, right? Later on, we're going to have isentropic efficiency on turbines, so we're going to calculate our ideal state 4, and then we're going to reverse back to the actual state 4, just like we did with the Brayton cycle. But for now, it's ideal system, so we can go ahead and do this. And then what we're going to do is we're going to look on table A5. We're going to look at 15 kilopascals. We're going to look for the 6.9 to see what's going on. So 15 kilopascals is right here. Entropy is the last two columns, so we're going to be looking at this value here and this value here. And we're going to note that 6.9 falls between these two guys here. And because it falls between these two guys here, it means that my state 4 is a mixture. Okay, so it's a mixture. So remember the drawing that I said, oh, I'm not sure whether it's going to be outside the dome, right on the dome, inside the dome. Now we know it's going to be right inside the dome. It's going to be something like this. All right, so my state 4 is going to be right there. Okay. Okay, what's the quality? How much vapor do I have, and how much liquid? Why do I want to know that? Well, because if we know a couple of things, right? We know if we're after the enthalpy of the fourth state, we know that's going to be a combination of the liquid, 1 minus enthalpy minus quality, and the vapor, saturated vapor, times the quality. Now, this we can grab from the table, this we can grab from the table, but this we don't know yet. So if we find the quality, we can find our enthalpy 4. And we know that, you guys probably sick and tired of this, but just one last time, you know that the entropy is also a combination of liquid 1 minus x plus vapor times x. And in this case, we know the saturated vapor from the table, we know the saturated liquid from the table, and we know S, right? 6.9. So the only unknown here is X. So you guys can go ahead and do the savvy way and just plug in straight what this guy is going to render, which is just S minus S liquid, S vapor minus S liquid. You can do that straight off, or you can do from this equation go into this. Okay, up to you. This renders, what do I have here? 85.43%. Okay, so we have about 15% liquid, 15% vapor. Out of that turbine transformation there when we had third state after the turbine, only about 15% of that actually transformed back to liquid. So think about it, if we were to put this back into the compressor that was before dealing with only liquid will have to deal with 85% of vapor, right? So that's why we need a condenser afterwards. Now that we know X, we can go and plug it in here, right? So H of liquid we have from the table, H of vapor have from the table, X we just grabbed, it's going to be 0.8543. So my enthalpy for state 4 is 2252. Okay, so we just defined all 4 states. So going back to your question, yes, you could have done that for the entropy, that would be fine, but that was going to render a lot of more work than just doing this, which is a quick way out, right? And you'll see that the difference is pretty much non-existent. If you guys want to take a screenshot, go for it. I'm about to change pages. Just want to point out that we now have enthalpy of state 1, 2, 3, and 4. So the next part is pretty trivial, right? Just use that information to finish it off. Okay, so if you guys recall, what we're looking for is the overall efficiency, which is a combination of all the efficiencies. Cool. And what we don't have is a thermal efficiency for our cycle yet, but that now we can calculate, right? Because thermal efficiency of our cycle will be, we can do work over energy in, or we can do Q in, Q out. Okay, so let's calculate Q in, Q out for the sake of it. My Q in is when I go from state 2 to state 3. That's going to be my enthalpy 3 minus my enthalpy 2, which is 3,000. That's the 3,500 that we had from third state minus my 200 that I had from my state 2. So that's 3298.6. And my Q out is when I go from 4 to 1. You guys can do positive, you can do negative, whatever rocks your boat. Let's do end state minus initial state. Let's do negative. Keep you guys on your toes. So that's the 2,200 that I just found minus those 200. So that's going to be 2,026.8 kilojoules per kilograms. Awesome. So now we have Q in, Q out. We're welcome to calculate work if we want to. We know work output is just going to be Q in minus Q out. This minus this is going to be about 1,200 or so. 1,271.8. And we can use this information over here. That's going to be, change color, didn't do it. My efficiency is 1,271.8 divided by my Q in 32. 98.6. My thermal efficiency is 38.56%.
Pablo, just a quick question, sorry.
Yep.
If we do Q in minus Q out, wouldn't that render to like be 5,000, like around 5,300 rather than 1,200?
Okay, good question. All right. So this is one of those things that you guys need to know what we're doing, right? You need to understand what's being said. So the Q out, you can think of it as this. You think of this area here, right? And the Q in is going to be, do a different one. This area here. All right, the negative is telling you that Q is going out. So my actual work is the area inside the curve. So it's going to be this area here. If you think about areas, it's probably easier because area is energy in this graphical form here. And if we want that blue hashed part here, there, what we need to do is take all the one from 2 to 3 and subtract the one from 4 to 1. Okay? In quantities, that's easy. That's going to be the quantity, this big area here is about 3,200 or 3,300. And the quantity of this smaller area down here is 2,000, right? So if I want this area here, it's just one minus the other. Okay, that's why I always tell you guys to watch out for your negative signs. You could have done this, right? Q out is just H4 minus H1, which is positive 2,026.8 kilojoules per kilogram. I always tell you this is redundant to say Q out and negative, right? So in this case, if you have a negative, you could say it's just one plus the other, because that's going to be negative. So don't forget what you're trying to calculate, why you're doing what you're doing, right? You're trying to find out that area there, which is the work output. The work output is just a measure of how much energy you put in and how much energy went out, right? It's just like a pot. You put $3,000 in and you took $2,000 out. So you have $1,000 left, right? So watch out. If you're putting $3,000 in and you're taking $2,000 out, you're not going to have $5,000 by the end of it.
Yeah. Okay. Thank you very much.
It's the same idea. Just that's like in terms of math, that would be it. But you need to make sure that you know what you're doing, right? You need to make sure that you understand why work is just a relationship between these two guys here. It's the same thing as when I told you guys about our first law of thermodynamics. That this guy, if you just consider this always as positive, that will get into you could get some wrong answers. So it can be positive or negative, but if you think of it that way, it's going to be even more confusing. So just think about whether we're going upwards in energy and energy is leaving the system or energy is going into the system. At least makes you guys know exactly what you're doing.
Awesome. Thank you.
All right. So I had another question here, which is, this 38% is only for the cycle. That's 100% correct, right? So this 38% is, okay, only accounting for the energy that the boiler already has from the coal. It can output from the turbine 38% of it. This is not for the whole thing, right? So the whole thing is going to be generator times the coal times this 38%. So generator is 96%. Coal one is 85%. Yep. And the thermal one is 38.56. So the overall thing is 31.46%. Okay, so that means that what we're doing if we take a step back and think about what is happening here is we're putting coal, we're extracting electric energy, right? So we're using the chemical energy of the chemical bonds from the coal and transforming that into electrical energy. And out of all the coal that we put, only about 1/3 of that energy is actually being extracted by the end of it as electrical energy. Our main bottleneck is the actual power plants. So if you guys wanted to improve this, you can focus on this guy here, which is your main bottleneck. If you can be able to improve this, everything else improves. Obviously, if you can get small improvements on all of them, it's even better. But then we're not finished, right? Because problem when goes on and it asks us, what is the required rate of coal that needs to be supplied for this guy to output the 175 megawatts? Okay, so let's do part B now. Let's do part B now. Okay, so part B is the following. Okay, my guy is outputting 175 megawatts. That's what my plant is outputting. Okay, And the fuel for this is coal, which has a CC, that's the specific heat of coal, of 29,000. Right. So now that we know the overall efficiency, we can use this to see how much actual coal power, let's put it that way, we need to put through. Because we know that the efficiency is a measure of how much we get out over how much we put in. Okay. So how much energy, let's put energy in the form of Q, are we putting into this whole system? That is not here the boiler giving to the water, but we're actually given how much coal energy we're giving in the beginning and how much we're actually taking away as electricity, right? So how much useful work, useful energy we're getting out of electricity, right? So in this case, what we're getting out is 175 megawatts, and I'm going to leave that in power to get power here, and my efficiency is 31.46%. So my QN, total amount of energy I have to put into this system, is going to be 175 megawatts divided by 0.3146, which is 556.26 megawatts. Okay, so what are we saying? We're saying that we need to put energy at a rate of 556 megawatts of coal into this power plant, to this vapor power plant, to obtain by the end of it 175 megawatts. Okay, so if we're putting this in terms of coal, what we can do now is relate this to how much coal gives in energy. Okay, and just look at the units, we have megajoules per second, and we have kilojoules over here, so we can eliminate those joules and just be left with kilograms per second, which is mass flow rate. So just working on our units, that's going to be this guy divided by that guy. So 556.26, and I'm going to convert mega into kilo, so it's kilo on both. So that's going to be times 10 to the third kilojoules per second, right? Kilowatts, same thing as kilojoules per second, divided by 29,300 kilojoules per kilograms. Note that my kilojoules go away. I have seconds on the bottom and I have kilograms on the top because it's dividing the division, so it goes up above. So that's going to be 18.985. Probably approximate that. About 19. We need 19 kilograms per second of coal going into this power plant, so that not 85% of the energy from the coal goes into the boiler that can give energy to our water, and the boiler through the whole process can get out about 40% of that energy into my generator, and the generator can get about 96% of that energy to my output as 175 megawatts. Okay, let me stop recording, see if you guys have questions.